after talking quite a bit about adaptations and what is beneficial in an environment and how we determine that, we need to start looking at the bigger picture. So we can look at individuals, we can even to some extent look at populations, and what we would like to be able to do is extend those observations into some sort of a quantitative model to be able to figure out at a population level how things change, whether things are staying the same, if there's no natural selection working on a trait. How do we do that? Now, going all the way back to Mendel, we've been able to do that on a small individual basis, looking at a single reproducing couple and the offspring that they produce. And so hopefully you're familiar with Punnett squares. There's a diagram of one up here in the upper right-hand corner. If you're not familiar with Punnett squares, you need to go back and review that. Let me know if you do need that. If I have enough students, even if I just have a couple, I can do it. And I can do a short review video. This is going to be essential, and not only just kind of knowing how to do a Punnett square, which is important, but why it works. That's even more important. If you understand the why, then the how is really easy. Okay? But a Punnett square is a prediction for the offspring of two parents. Now, I will do the 1-minute version right now, but if you need it in a little bit more detail and need some information about the why the Punnett square works as a prediction for offspring, let me know and I'll do a little bit more in depth. So basically what we do is we take advantage of simple probability. If you have two alleles, then what is going to occur is when you make your gametes, whether you're making eggs or sperm, about half of your gametes will carry one of the alleles, and about half will carry the other allele. Now, this is from the book. There's a little bit of an issue here. I don't know why they made that A2 blue. That A2 should be red. And they've used both numbers and colors here to designate the different alleles, okay? But you have a 50-50 chance. So this is what's called a heterozygous cross. You have one parent with an A1 allele and an A2 allele, the other parent with an A1 allele and an A2 allele, okay? So when they make sperm, when they make eggs, there's a 50-50 chance. And basically, if we want to figure out what their offspring are going to look like, all we have to do is look at all the different populations. It's kind of like flipping a coin. And they realized that fairly early on, they realized that you could predict by looking at a simple union of probabilities. And so to do this mathematically, you look at the probability as some value between 0 and 1, with 0 meaning there's no possible chance it occurs, and 1 meaning it's a 100% chance that it occurs. And so if you have two alleles, it's a 50% chance of having one allele when you have an offspring, and a 50% chance of having another allele. And now the union of two probabilities is simply the product of those probabilities. Now, if that makes your head spin, sometimes math does. It's rather simple. So let's put it up here mathematically. So here is how we represent the union of probabilities. Oops. Let's come back here. Okay, so the union of probabilities is equal to, and we're going to say probability number 1, so P1 times, right, that's what the product means, probability number 2. And remember, these are always expressed as values between 0 and 1. So if the probability of getting an A1 allele is 0.5 and the probability of getting an A2 allele is 0.5, then the union of those probabilities is 0.5 times 0.5, and if you do that mathematically, it's going to be 0.25 or 25%. Now, a Punnett square is a visual way to represent those unions of probabilities. Okay, so we put those two together. One square represents 25% of the 4 squares, so the chance of having two A1 alleles is 0.5 times 0.5 or 0.25, 1 out of 4. So Punnett squares are a nice kind of visual way to do this probability of mathematics. Now, Hardy and Weinberg independently, so that's why it's called Hardy-Weinberg, they both worked on it separately and figured it out, realized that this could be applied not only to couples, but it could be also applied to entire populations. Now, to do this at the population level, we have to make a couple assumptions. The main underlying assumption is that we can treat individual alleles as if they are randomly drawn from a large pool of alleles, and the pool of alleles is represented by the entire population. Now, there are some stipulations for us to make that assumption, and we'll look at that. There are actually 5 assumptions, and we'll look at that at the very beginning of the next discussion. Okay, but for now, let's just take it for granted that we can treat individual alleles in a population rather than treating them as connected to another allele inside an individual. We could treat them as random events being drawn from a population. Okay? And so to do this, basically, the next slide, we break up those alleles. Now, the benefit of this is that we can look at populations with different values of these alleles. So here what they are doing is they're counting up all of the alleles in different populations of these beach mice. And they're seeing in some areas they have only one allele. So they counted 20 individuals. Every single individual in this population carries one allele, represented by the blue color. But in this one, 20% of, they counted 20 individuals. And about, that's maybe a third, 33% of them carry the green allele. And in another individual population separated by this large bay, that's like 95% of them carry the green allele. We see very different allele frequencies. But there's a general trend where in the middle we have this allele, and on the margins of the population we tend to lose that allele. Okay? And so we can move from a qualitative, right, saying, yeah, generally this allele is better in this environment, or this allele is better in a different environment. We can move from that and we can begin to put numbers on it and actually estimate how much better it is. Okay, so we're going to now extend these probabilities to a large population rather than individuals, and we'll show you how we do that. Now, to do this, we're going to both use the union of probabilities, which we already talked about, and we're also going to use another simple one where it's not both occurring, but one or the other. And in that case, we add them together. And these are both rather simple. So in other words, if I ask you, if there are only 2 outcomes, heads or tails, and I ask you, what is the probability of me getting a heads or a tails? And again, we're going to assume it won't land on its margin. That's an impossibility. The coin won't land standing up, so it's got to land flat. Okay. So then you say the probability of getting a heads is 50%. The probability of getting a tails is a 50%. I add those together and I get 100%. So it's a 100% chance that you get a heads or a tails. But if I say, what are the chances that I get a heads in my first chance and then I get a heads in my second chance? Well, that's not 100%, right? So you have a 50% chance of getting your heads in your first flip, and then you get have another 50% chance of getting your heads in your second flip. So that's the union of probabilities. Now, this second one, so we talked about the union, but the second one is called the intersection. You don't really need to know those names, but hopefully you understand mathematically how those work. So if we have more than 2 outcomes, we can still do it. So we could say if there's a 1 in 6 chance of rolling a 1 on the first die, and a 1 in 6 chance, assuming it's an evenly balanced die, right? Both of them are evenly balanced. Then all you have to do is say, well, 1 in 6 times 1 in 6, and that would give me the probability of rolling snake eyes. So 1 out of every 36 rolls, on average, you're going to roll snake eyes, right? A 1 on both dies. Now, some numbers, like 7, have different numbers of combinations. So if we're going to figure out the probability of rolling a 7, then we need to now use both union and probability. Now, we don't really care about dice for this class, so I'm not going to get details of how to do that, but we're going to look at this for alleles in a gamete pool. And so here is the key leap in logic that both Hardy and Weinberg figured out. We could take a population of individuals that carry 2 alleles each, and we can treat them as if each of those alleles are independent. Now, the reason we can do that is, number one, because of random assortment. Because when individuals make gametes, those are evenly distributed. All of your alleles are evenly distributed into those gametes. And so that means there's basically random sampling at that level of meiotic division. Now, there are some other assumptions. Again, we'll look at those 5 other assumptions at the beginning of the next lecture. okay? And so those randomly are paired together to make the next generation. Now to do this, there are two values that you need to keep straight in your head, and we're going to do several examples of this to wrap up this lecture. The first is the genotype frequency. So genotype frequencies, again, are just a number between 0 and 1, representing all of the genotypes in the population, okay? So in this very small sample, genotype frequency, we have one heterozygous for the A2 allele, homozygous for the A2 allele, two that are homozygous for the A1 allele, and three that are heterozygous. So we could count those up and very easily figure out a number. So this would be 20%, right, of them, 1 out of 5, or 20% are homozygous for the A2 allele. 40% are homozygous for the A1 allele. And then that would leave 60% that are heterozygous. And so we would say 0.2, 0.4, 0.6, right? Again, mathematically rather than percentages, we always represent them as frequencies between 0 and 1, okay? So that's the genotype frequency. But from there, we could fairly easily figure out the allele frequency. And allele frequency is just the same, except we're just going to count alleles. So we count up 1, 2, 3, 4, 5 of the A2 alleles, and we've got 1, 2, 3, 4, 5, 6, 7 of the A1 alleles. Now notice, and on this diagram, I don't know why they did this. This is an awful diagram. We have 10 alleles over here, but then suddenly over here, we've got 12 alleles. Oh, I'm sorry, I was wrong. That was correct. We've got 12 alleles. Okay, good. The diagram's not as bad as I thought. We have 12 alleles here, and we have 12 alleles there. Now, no matter what the total volume is, the total number of alleles at the end, the math always works out. But if you have nice round numbers to start with, the math's just a little bit easier. In all my examples, I'll use nice round numbers, 100 or 1,000 or something like that. I don't use small numbers, and there's a reason for that. And the reason is, with very small numbers, you get much, much more sampling error. And that's really important, right? So imagine I flipped a coin, and I said, I'm going to flip a coin twice. And I flip it, and I get heads, and I flip it again, and I get heads, and I say, aha, see, this coin is an unbalanced coin. It's not a fair coin, because it always lands on heads. Well, hopefully you'd look at me and say, no, your sample size is too small. Flip it 100 times or flip it 1,000 times, and then see what your outcome is. And then we could have a better estimate as to really how biased, if it was, how biased that coin was. So sample size is important. But if we use nice round numbers in our sample size, the math is just a little bit easier. Now, we are going to run through several examples of Hardy-Weinberg equilibrium. We're going to start with genotype frequency. I'm going to teach you a very simple way to figure out the allele frequency if you are given a genotype frequency. And then we can take that allele frequency and plug it into the Hardy-Weinberg equation. If you memorize the Hardy-Weinberg equation, that's enough, but you do need to know it or have it written down, I guess, for exams, since your exams are online. But you do need to know how to implement the Hardy-Weinberg equation. But I'm also going to teach you why the Hardy-Weinberg equation works. We're going to kind of, not really derive it, but a little bit. We're going to go through it in a explanatory mode to show you why the Hardy-Weinberg equilibrium works, okay? Now, again, if you don't know why it works, you'll still be able to do okay on the exam, but knowing why it works helps you connect these concepts and will really, I think, help you understand other concepts that we're going to be going over. So that's why I do the why. So let's start with an example. We'll work through one example, and then we'll talk about the why this Hardy-Weinberg equation works. So let's say you go into a population and you sample 1,000 individuals randomly in that population. And 1,000 is a pretty good sample. You can get usually pretty accurate results with 1,000 individuals in your sample, assuming you're sampling fairly randomly. So I go in and I sample and I get 250 homozygous dominant. I get 500 heterozygotes and 250 homozygous recessive. Now you're having flashbacks either to Bio 1 or maybe it was in Bio 2 or genetics, but hopefully you've seen this before. So you need to make sure in your head you know what homozygous means. Hopefully that's pretty simple and you've got that down, what heterozygous means, right? In all of our examples for the ones that we do quantitatively, we're only going to do 2 allele systems. But you should recognize that sometimes it's a little bit more complicated where we might have 3 or 4 or more alleles for a single gene. But for our purposes, we can illustrate everything we need to with just simple 2 allele systems. So you can either have a big A or a little a. Every individual is diploid. We'll always do diploid examples because most of the organisms that we're going to be working with and many of the organisms that we come across on a daily basis are diploid. But again, there are exceptions to that rule. Okay, so we want to take these genotype numbers, which we can very easily turn into frequencies, right? If you have 1,000, it's easy. The frequency of the homozygous dominant is 0.25, 250 out of 1,000. The frequency of the heterozygotes is 0.5, and the frequency of the homozygous recessive is 0.25. Okay, hopefully that's pretty straight and simple so far. Okay, straightforward, I guess, and simple. But we need to take these genotype numbers, this raw count of genotypes, and turn them into allele frequencies. Now, mathematically, the frequency of one allele is represented with the letter P. The frequency of the other allele is represented with the letter Q, but I've written both of them for now. In the future, we'll probably just put P and Q. Just remember, P is the frequency of one of the alleles. By convention, the dominant allele. Q is the frequency of the other allele, and again, by convention, Q represents the recessive allele. But those are just conventions. I always used to ask my algebra teacher, why do we always use X, Y, and Z? And we didn't always. Sometimes, for algebra, use A and B, but it seems like X, Y, and Z, those are the go-to letters. And there's really no good explanation. It's just whatever the first people chose, and it's just kind of been picked on. It could have just as usually used L, R, and I don't know, W or something, and you'll see those sometimes. It's just a randomly chosen number to stand in. Okay, so P is the frequency of the big A allele, Q is the frequency of the little a allele. Okay, so how do we do this? Now, there is an equation. You can look it up, or if you really love equations, I'll teach it to you later, but I'm not going to do that in a lecture unless you really, really want to memorize another equation. I'm going to show you the way to do it intuitively. Okay, so let's open this up and let's do this intuitively. So the allele frequencies for this population. What I'm going to do is I'm going to count up all of the homozygous dominant, right, 250 individuals, and then because they carry 2 copies of that big A allele, I'm going to times that by 2. So I'm going to do 2 times 250. And again, the reason I'm doing that is those 250 individuals carry 2 copies of that big A allele. Okay, I'm now going to add in the heterozygotes. Now, I only add them in once because these 500 heterozygotes only carry 1 copy of the big A allele. So what I've done here is just simply added up all of the big A alleles in my sample. So I have 1,000 big A alleles. Let's make these a little bit smaller so that we can see it all. Okay? So that is the frequency of the big A allele. Now this one's nice and easy because it's symmetrical. We'll do some asymmetrical ones and show you. It works still the same that way, but this one's just a little easier. 2 times 250, because I have 250 individuals that carry 2 copies of the little a allele. And then I add in the heterozygotes. So I get 1,000. Now, to figure frequency, it's easy, right? If I have 1,000 boys in a classroom and 1,000 girls in a classroom, or we could use any example, we're going to end up with a fairly simple frequency. All we do is divide by the total. So we divide by 2,000, and I get a fairly simple frequency for this. Let's make this consistent here. So my frequency of my big A allele, which is again P, is equal to 0.5. And this one, P, is equal to 0.5. Now, when you're dealing with 2 alleles, sorry, that should be Q. Your Q is 0.5. So when you're dealing with 2 alleles, these 2 numbers are always going to sum to 1, right? Because this is an intersection. What are the chances when I sample an allele from the population I get a P or a Q? Well, since P and Q are your only options, it has to sum to 1 or 100%. Okay, so we've got the allele frequency. So if we were to answer this question, we could say allele frequencies. P is going to equal to 0.5. And again, usually just by conventions, it's lowercase. So we'll change that since it's trying to capitalize it for me. And Q is equal to, still capitalizing, 0.5. Right? Okay, so hopefully that made sense to you. If not, we're going to do one more example here. We'll do other examples on the next worksheet. So you're going to get familiar with this. You need to practice with this. You're going to see it in an exam, and you'll see questions about this. And again, the key is don't mix up. In fact, let's go back and just make this a little easier to see. Let's put all of this over here. How's that? Maybe put one more there. I'm running out of space. Anyway, we can do this. There we go. That'll make me feel a little bit better. There's a line through that one word there. But so that's how we do this. Okay, so we end up with this fairly nice, simple p-value and q-value. Now you're like, okay, great. What good is that? Why did I do all of that math? Well, if we know the p-value, right, which is a frequency of the big A allele. So remember, p is frequency of big A allele, q is frequency of little a allele. If we know those, then with some basic underlying assumptions, we can predict what we should see in the next generation. And this is the breakthrough that Hardy-Weinberg had. So here's how it works. We now have our p-value. We have our q-value. Let's predict into the next generation. So what is going to be the frequency of the big A in the next generation? What is going to be the frequency of the big A, little a, the heterozygotes in the next generation? Now, this was the insight of Hardy-Weinberg. They realized that the frequency of the big A is going to be the union of the big A, the probability or the frequency of the big A allele. Now, again, the language here sometimes, if you're not familiar with probability language, can be a little bit off-putting. But let's just maybe put it in simpler terms. If I make an individual, what are the chances that they get a big A from mom and a big A from dad? And so all we have to do is times the probability of the big A's in the population together. Now, if we knew mom and dad, it would be easy. But remember, we're trying to make predictions over the entire generation. So I'm not talking about one specific individual. I'm talking in general, when a baby is born, what are the chances if it comes from that population that it has a big A, big A? And so we do the union of probabilities. And so I would do P times P, right? Or mathematically, right? P times P is represented as P squared. Let's make that a superscript. Cancel how I'm on the. Sometimes Word and any Microsoft things are just so, anyway, not very easy to do certain things. So p squared, right? So of course in this case it's 0.5. We'll write the whole mathematical equation out here, times 0.5 or let's do it this way, right? 0.5 squared. Same thing as 0.5 times 0.5. And again, we need to make that a superscript. And there we go, font, superscript. Yeah, font, there it is. Okay, so 0.5 squared, which is 0.25. So we are predicting that 25% of the next generation should be big A, big A. Now, for the other homozygote, it's easy. It's the same thing, but using the Q values. So I'm going to do Q times Q, which is equal to, of course, in fact, maybe this is the easiest way to do it. Let's just cut and paste the rest of this. Shortcuts, right? Q times Q, or Q squared, which is 0.5 squared, which is the same as 0.25. Okay, so homozygotes are pretty simple. All you have to do is the union of probabilities using that allele frequency as your probability, your P and your Q value. Now, this one is a little bit trickier. To do this, we need to figure out what is the probability of you getting a big A from mom and a little a from dad. And so we say, well, we know those frequencies. It would be the probability of getting a P times a Q, right? Just the union of probabilities. Now, you could also be heterozygote if you get a big A from dad and a little a from mom, the reverse, right? So you could do that, but to do that, we need to add in, so it's the probability of having mom and dad times, I'm sorry, plus, right? Because this now is the intersection of getting a Q from mom and a P from dad, right? The reverse of what we did over here. Now, if you look at that mathematically, right, remember order of operations, this is not really important, but the why I think will help most of you understand it. So the probability of getting a P from dad and a Q from mom and vice versa is represented here. We put these together. We can simplify a little bit. I'm going to make this a little bit smaller so I can fit it all in. Okay, so when we simplify that equation, all we have is now PQ plus, which is P times Q, right, plus QP. Now you guys are having flashbacks to algebra and like, oh no, algebra. It is a little bit of algebra, but I'm not going to make you derive these equations. I'm just explaining them, so hopefully they'll make sense in your brain a little bit more. Now, P times Q and Q times P, we recognize those are the same thing, so we can write them both the same way. So we have the probability of a heterozygote now as PQ plus PQ, which is 2PQ. Okay, so in this case, 2PQ is simply 0.5, right? I'm sorry, 2 times 0.5 times 0.5. I'm going to run out of space here. And that equals 0.25. Sorry. 0.5. You can check me with a calculator. So 2 times 0.5 times 0.5 is equal to 0.5. We'll make those just a little bit smaller. I think you can still read them. Now we're done typing, we can make them large again. Okay, so that's a long explanation, but almost a derivation of where these numbers come from. Okay, again, hopefully that makes sense in your head. So again, very quickly, the probability of being homozygous dominant is the probability of a big A times the probability of a big A, or the union of those probabilities, which is equal in this case to 0.25. Same thing for the homozygous recessive, except with the Q values. Okay, the probability of being a heterozygote, we have two ways you could be a heterozygote: big A from dad and little a, or big A from dad and big A from mom, and then the other allele coming from the other parent. So it is the union of those two probabilities, then the intersection or added together, and that's what we get. Now notice these numbers sum to 1. And they will always sum to 1 as long as your probabilities sum to 1. Your outcome in the Hardy-Weinberg equation will always sum to 1. So the way that we write this, and I'm actually going to make one more modification here. We're going to do this next example. The way that we write this is we say P squared, and I'll make these subscript here in a little bit. Sorry, superscript here in a little bit. P squared plus 2PQ plus Q squared is always going to equal 1. And that is the Hardy-Weinberg equilibrium. So superscript, I'll get here so it'll look nice and pretty. Let's see if it will let me repeat. There we go. Okay. So that is our Hardy-Weinberg equilibrium. P squared plus 2PQ plus Q squared equals 1. Now, one very common mistake, I don't want you to fall into this trap, is that when people are doing Hardy-Weinberg, they plug in their numbers and say, if it equals 1, then Hardy-Weinberg equilibrium is in effect. That's not true. In fact, these numbers will always equal 1. That's not how we tell if Hardy-Weinberg equilibrium is in effect. We'll look at that in a little bit. In the example we just did, so here, Hardy-Weinberg equilibrium is in effect. So in fact, let's do that now. How do I tell? What we do is we look and see, did our predictions for the next generation match our original observations? And in this case, they do, right? We have 25% of the population we're predicting will be big A, big A. The parents, 25% of the parents were big A, big A. 50% heterozygotes, 50. So notice everything matches. So that's how you assess whether or not populations are in Hardy-Weinberg equilibrium. Let's do one more example. Now, what you should do is pause the video and try to work through this yourself. In class, I'll have you work in pairs. If you've got a friend, if you want to call over your little brother or little sister, your mom or dad, your significant other, whoever is there, just come over and say, hey, let's do something really fun. I'm just kidding. If you want to, you can, but work this out. Pause the video and then come back and let's do it together. All right, so here's how it works. Again, we're going to do it very, very simply, straightforward, the same way we did it already. We want to figure out the p-value. So I'm going to do 2 times 40 because there are 40 individuals that carry two copies of that big A allele. Then I'm going to add in 320 individuals that carry 1 copy of that big A allele. And so I get a total of 400. For the Q value, 2 times 640 plus 320. So I have 1280 plus 320, 1600. Let's make these fonts smaller so everything fits on one line. So here we are. I now have the raw count for my number of big A alleles, my number of little A alleles. All I need to do is turn those into a frequency. And again, to do that, we divide by the total. So I have 400 big A alleles, 1600 little A alleles. It's divided by 2000. Now again, because we started with nice round numbers in our sample, the math's a little easy. Now, don't worry, well, I guess especially since you're doing this online this year, but even if you weren't in class, I let people use a calculator. So if you want to use a calculator, great, but you're going to need to be able to go through this situation for Hardy-Weinberg. So we're going to go through a couple examples. We'll probably do one more today, and you'll have some on the worksheet. There'll maybe be some other guide videos if you're having trouble and need more practice. So all we do is divide by the total. So we're going to come back in, we're going to say divide by 2000. And we end up with, might have to make the font even a little bit smaller, we fit it all on one line. 2,000. 400, of course, divided by 2,000 is 0.2. And you can double check me if you want, but that's, it's not, again, the math's not too bad, but if you're having trouble, if you're brave, do it by hand. If not, use a calculator or just double check yourself with a calculator. Same thing here, right? We're going to take 1,600. We're going to divide by 2,000. And I end up with a value of 0.8. Make this one a little bit smaller, fit it all in one nice line. There we go. Okay, so again, we've done 2 examples now, but you need, if you are given a sample from a population with genotype counts, you could turn them into frequencies if you want, but that's not really our end goal. Our end goal is to take those counts and turn them into allele frequencies. Okay, now that we've got it, all we have to do is plug them into our equation. Now, I'm not going to go through the explanation, derivation again, the union and the intersection and all that fun stuff. As great as that is, at this point, all you need to do is remember the equation. So p squared, right? So what are the allele frequencies in our population here? Oops. I erased that one. Let me get back here. So the allele frequencies in this population, I don't know what I did. Somehow I went back in time. Oh, well, that's all right. Won't worry about it now. Okay. So the allele frequencies for this population are going to be 0.2 and 0.A. I'm going to plug them into my equation now. So I'm going to do p squared plus 2pq plus q squared. Let's go ahead and plug that in. In fact, we'll copy that, paste it again down here just so you can see. We'll put it right above it. And now let's just plug it into the equation. So of course, p squared is going to be 0.2 squared. Woo. Sometimes PowerPoint is not my friend. Okay, 0.2 squared plus 2pq, which is going to be 2 times 0.2 times 0.8 plus 0.8. Make this nice and happy. My math teacher is going to be much happier with me if I make this nice and clear. And then equals, now let's make these so it's not confusing. Let's make these superscript. So it's to the power. There we go. Let's take a look at it. Move it up just a bit. How about that? It's a little easier to see that way. There you go. So 0.2 squared plus 2pq plus q squared. And if you notice, this is always going to sum to 1. So no matter what I do, as long as I've started with the correct numbers, we're always going to have that equal 1. That's not what we're testing. But what we are testing is do these. So remember, p squared is a prediction for homozygous dominant. 2pq is a prediction for heterozygotes. And q squared is a prediction for homozygous recessive. So we just check to see if it matches. 0.2 times 0.2 is 0.04 or 40 out of 1,000. Yep, sure it matched. This is going to be 0.2 times 0.8 is 0.16 times 2 is 0.32 or 32%, 320 out of 1,000. So again, everything matches. We are in Hardy-Weinberg equilibrium. So in both of these examples that we've done, we are in Hardy-Weinberg equilibrium. So when we predict the frequency of the next generation, it matches our original observations. Okay? Now, I'm going to do one more example. This one's not on the PowerPoint, but it's worth going through. If you feel comfortable and happy about it, you can pause the video now. This is actually the end of this video. If you don't, let's go through one more example. Okay? So I'm just going to put random numbers. Well, these are really not random. I know what I'm doing, but I'm going to put some numbers up here. Let's say we had, and I'm going to make them nice round numbers. Again, you could do really any numbers. It's just the math is a little trickier. But let's say we had 400 homozygous dominant. We had 400 homozygous recessive. And we have 200 heterozygotes. Let's get rid of our previous estimates. And let's run through this process again. Okay? So pause the video. Take a minute to do it. Remember, count up all of your big alleles. Count up all your little alleles. Divide by the total, which, because we have 1,000 individuals, the total will be 2,000 alleles. And get your p-value and your q-value. Plug that p-value and q-value into your equation. And then look to see whether those 3 different parts of the equation match the 3 genotype frequencies. So pause the video and do that. Okay, here we are. If you're having trouble remembering why I'm using these numbers, go back and look at the previous examples. Now this is nice and easy. Again, it's a symmetrical example. So the math is easy. Once you've figured out one, you've figured out the other. So 2 times 400 is 800 plus 200. So we get these nice round numbers. This one equals 1,000. All right, so equals 1,000. All we have to do is divide by the total again, which is 2,000. 1,000 big A alleles, 1,000 little a alleles. We divide by 2,000. And I end up with a value of 0.5. Same thing on this one. Nice and easy, right? Now, the last step when you're doing Hardy-Weinberg is to compare. Plug them into the equation and compare. So let's do that. And I'll overwrite this. So we will do q squared, which is going to be 0.5 squared plus 2pq, which is 2 times 0.5 times 0.5 plus q squared, which 0.5 squared. And again, it's always going to equal 1. That's not what we're testing here. Let's make these superscript. And so let's take a look at this final equation. Now, this looks familiar. This is just like the first example we did, right? So we're predicting in the next generation we should see 0.5 squared, or let's go ahead and 0.25, right? 2 times 0.5 times 0.5 is going to be 0.5. And then 0.5 squared again, 0.25. Again, it's always going to equal 1. But that's not what we care about. We care about whether this matches our original observation. So we're predicting in the next generation 25% of the individuals should be big A, but our original sample had 400 out of 1,000, or 40%, so it doesn't match. We predict 200, we observed 200, but our prediction says no, next generation should be 500. It doesn't match. So this population is not in Hardy-Weinberg equilibrium. And in the next discussion, we'll talk about what that means.